Hello, good morning. So here today in this video we'll be talking about wedge shaped thin film. It is the first experiment of this semester, wedge shaped thin film. First of all, let's understand this title. It is made up of these two terms, wedge shape and thin film. Let us know what is wedge shape. You must have learned theory in more detail in the theory classes. But here let's just briefly talk about the theory and we will see more discussion or we will dedicate more time on the demonstration and procedure of this experiment. So wedge shape. You know what is a shape? This wedge shape. What is wedge shape? This kind of shape is a wedge. Is a wedge kind of wedge shape. Okay. And other term is thin film. We have discussed in class, thin film is an optical medium which is very thin. Very thin means what? Its thickness is in range of few micrometers. Okay, so this is kind of a wedge shaped thin film. So its thickness should be in range of few micrometers. So how I can create an optical medium or a thin film which is having thickness in range of few micrometers? So see, this is my wedge shape. But how I can create a wedge shaped thin film or an optical medium having wedge shape with thickness in range of few micrometers. So here how you can do it. First of all, I will take one glass plate. Let me draw it perfectly horizontal. Glass plate might be having thickness in few millimeters, that's fine. Okay, this is my one glass plate. Over this glass plate, I will take another glass plate and keep it like this. One end of these two glass plates are touching to each other. But on another end, I am putting some spacer here. A spacer with thickness in range of few micrometers. Let's say a paper. Paper must be having thickness in few hundreds of or few tenths of micrometer. Or human hair. It will be having thickness in few tenths of micrometer. So I can put one human hair here and other end I'll be tying it together so other end is touching to each other. So what is thickness here? 0 micrometer or 0 meter is the thickness at this point. But what is thickness here? Thickness of this film is equal to thickness of this spacer. Or I should say diameter to diameter of this. Now, what you got between these two glass plates and medium? What is medium here? Right now, it's air. Right now, medium is air. So you got a thin film of medium air having wedge shape. Wedge shape means its thickness is constantly increasing. As you are moving toward right, its thickness is increasing. Its maximum thickness is equal to the thickness of the spacer. What is minimum thickness? At here, this point thickness is 0. So here, 0 thickness. In this experiment, our aim is to find thickness of this spacer. Means thickness of this human hair or thickness of this paper. That will be our aim. How to find it? For that, we are going to take help of some optical instruments. How we can do that? That we are going to do with the help of an optical phenomena. You have understood interference in thin film in the class. Okay. In wedge shaped thin film, when interference is occurring, you get some fringes. You get parallel fringes. This kind of parallel fringes. Equal size, parallel to each other, and equally spaced fringes. If we enlarge this, okay, this is the kind of image. If you enlarge it, I just showed for demonstration purpose. By studying these fringes, we will be able to know the thickness of the spacer. Let me directly tell you a formula. How this formula is obtained, that you will be learning in classroom. The formula of thickness of spacer is T equal to lambda into L divided by 2W. In this equation, T is thickness of this spacer, lambda is wavelength of light used. So in this experiment we are going to use sodium light source, and for sodium light source, you know, sodium light source is monochromatic light source. Remember what I told you about monochromatic light source? It's kind of light source which gives one wavelength. So sodium source is not ideally monochromatic, but it is close to monochromatic. It's giving yellow light only, and its wavelength, central wavelength, lambda is equal to 5900 angstrom. So I am writing these values somewhere here. Lambda is equal to 5900 angstrom. L here, the small l is length of this glass plate. In case of our physics lab experimental setup, the length of this glass plate is 4.5 cm. L is equal to 4.5 cm. How we can know this value? This is standard value. For sodium source, the wavelength given by sodium source is 5900 angstrom. How we obtain this value? How we got to know that it is 4.5? We just use scale. With the scale we got to know this value. It's simple. What about this W? Okay. W is fringe width. Fringe width. How thick this fringe is? How you can know fringe width? You can know thickness. You can find out the position between two consecutive fringes, and you can subtract their positions, and you can find W. If you find W, you can substitute all these values in this equation and find out T. But we know lambda, we know L, but we don't know W. We right now don't know W. So our job will be, first immediate task will be to find W. If we find W, then we can substitute values in this formula and find T. Okay, so now let's see how we can find W. Okay, what is W? It is fringe width. Let me write some. W is fringe width. These are fringes. Among here, there are bright fringes and there are dark fringes. So everything which is drawn with a red marker, I am representing their bright fringes. And the spacing between them is dark fringes. That means light is not reaching there. This red line are representing the places where light is reaching. White spaces, light is not reaching. So we are consecutively getting bright, dark, bright, dark, bright, dark fringes. Your job is to find what is fringe width. To find fringe width, you need to find this space. So look at this enlarged image. You are supposed to find this. This is your W. Okay, how you can find it? So this, can you use a scale? No. See, these are, I'm showing them space. I'm showing them apart. So what is W? It is fringe width. Fringe width. With red shaped pen, you are getting this kind of consecutively bright, dark, bright, dark. Here, all these red lines are representing bright fringes. Then the spacing between them is representing dark fringes. We are getting parallel lines consecutively, equally spaced. Look at this enlargement. Here, what is W? The spacing between two consecutive fringes. It is just representation. That's why you are finding these bright fringes as thinner and dark fringes as larger. But when you see actual fringes, that won't be the case. Bright, dark will be evenly spaced. Okay. Your job is to find this W space between two consecutive fringes. Now you cannot use scale to find this distance. You need some special equipment, and that special equipment is travelling microscope. You know actually how the setup is arranged. To observe fringes, this is your setup. You need to throw some light over it. You need to throw light from this above, this direction. Now, you also have to observe from this direction. So both of the things you cannot do from this direction. So here we are using a trick. We will be placing our sodium lamp at this place. We will use some slit and we will take some important part of the light. So, sodium rays will be coming in this direction. how I can divert it toward this direction? I'll place one glass plate at 45-degree angle. At 45-degree angle. So this light ray will reflect from here and they will fall perpendicular to this air film. When they go here, due to path difference, fringes are created. Due to constructive and destructive interference, fringes are created, and you are putting your telescope here. So I'm not having much space, so I'm drawing it very close here. So this is your human eye. So you are observing this reflection, light reflected from this direction and reaching to your eye with help of telescope. So this fringes will be very, very close. You require a telescope to separately see them. So we are putting one telescope here, and from telescope lens you are viewing these fringes and you are getting this image. In our case, the telescope which we have is special kind of telescope. It is called travelling microscope. As name is suggesting, it's kind of a microscope which can travel. Here the type of telescope which we are using is a special type of telescope. It is called travelling microscope. As name is suggesting, it's kind of a microscope which can travel. Means it can move, and that movement we can do very precise movement. And we can also know that how much we moved our telescope. So see, the simplest trick would be, look at this enlarged image of the fringes. I can do one thing. With this travelling microscope, one scale is also attached. So at beginning, I will place my marker at this fringe. Okay, there will be a lot of fringes. I will go to any of the fringe and I will start my measurement. I'll put my marker crosswire, that will be crosswire in this telescope. I align this crosswire on any of the fringe, preferably dark fringe. Why dark fringe? I'm not a racist, but dark fringe आपको sharply दिखेगी, इसलिए मैं dark fringe बोल रहा हूँ. We will align our crosswire on a dark fringe, and there is a scale attached with this microscope. So I will note down what is position on the scale of this crosswire. Later, I will precisely move my telescope and gradually move it toward this position, toward this fringe. If I mark or if I note down position of this fringe from scale, so I have position of this fringe and this fringe. If I take subtraction of both the position, I will get fringe with W. My job is done. I can substitute this value in this formula and I can get T. Experiment is over. There is a catch. If I do like this, then the value of W will have large amount of error. So I need to reduce the amount of error because it's very close distance. And how I can reduce the amount of error? By taking a longer measurement. So instead of measuring two consecutive fringes, why don't I measure thickness of 10 fringes, then later divide it by 10. So error will be also divided by 10. So this is a good technique. So I will measure this fringe thickness. I will measure the position of this fringe. Let me name it 0th fringe. Then I will measure position of 10th fringe. So 0th fringe, 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th. This is my 10th fringe. I will precisely move my microscope. I will move its crosswire from here to this fringe. I will bring it here. I mark down the position of this fringe. Now I have position of 0th fringe, 10th fringe. Okay. If I take subtraction of both the position, I will get thickness of 10 fringes. Thickness of 10 fringes. If I divided this value by 10, I will get value of W. Let's substitute that value of W here in this, and you get value of T. Job is done. Okay, fine. This is the thing we are going to do this, and not just one time. We will be doing this 3 times. So we will be taking measurement of 0 to 10, as well as we will be taking measurement of 0 to 10 to 20th fringe, and we will be doing between 20 to 30th fringe. So 1, 2, 3. Okay, maybe we can also take one more reading. We can decide it later how much readings we want to take. But now, right now, you can have this separation, this separation, this separation. All these separations will give you value of 10 W. You can divide those values by 10. You can get value of W. Now you have 3 values of W. You can take average, that will be your finalized value of W. You will substitute here. So this way you will get minimum error. Understood? Now the next task, how to take readings from. So here we will understand how to use travelling microscope. This is travelling microscope. Why it is called travelling microscope? First of all, it is microscope. Here you can see this is a scope which can magnify objects which are kept here. Now, why the traveling work? Because it can move along 3 axes. It can move along this axis. You can call it XY axis, or left and right it can move. It can move front and back with this. And it can move, we can also change its height with this dial. So this dial is used to change its position left and right. So I'm moving this dial. Can you see it's moving toward left direction? There is very minute change in position. So you may not be able to see here. If you look at the scale, you will see the difference. Okay, let me take it back. Now it should be moving right. With this dial, I can move it front and back. Yeah, this motion you can clearly see. And this dial is used to change its height. We have kept one graph paper here. With this microscope, we will be seeing this graph paper, how it's looking. See here. See, this is the image of that graph from microscope. Isn't it looking beautiful? Now can you see one cross wire at the center? One line, dark, very thin line. It is meeting at center. That is called cross wire. See, you will be able to see it now. It's horizontal line. Sorry, that's a vertical line. Now I want to know the position of one of the line. So I will move this dial and align my cross wire on this line. I can move up, down and left, right. I show you dials which are doing this movement. Now remember one thing. When you move your dial toward left, or I mean to say, when you see with your naked eye, if telescope is moving toward left, then when you see the image inside the telescope, it will be moving toward right, because you get inverted images. So please be careful and don't get confused. Now I have aligned my cross wire with one of the fringes. We'll be calling them fringes because we want to work with fringe. This is just demonstration of graph paper. I want to know what is position of this line on this scale. So look at this scale. This is the scale. I want to know its position. There are two things you can see. This is centimeter scale and this is vernier scale. I suppose you must have used vernier calipers in your 11th-12th. It's okay if you don't know. Here I'll be guiding you how to use vernier calipers. Here, this is main scale, vernier scale. Now zoom here. See this, on vernier scale we have one marker. Okay, that's your marker, or we can say 0 point. This marker is showing what is the value on main scale. Now see this, it's given, values are given in centimeter. This is 6 centimeter, this is 7 centimeter. Okay, now and this is 8 centimeter. See here, between 6 centimeter, 7 centimeter, you will find 6.5 centimeter. And this is 6.1 centimeter, 6.2, 6.3, 6.4 and 6.5. Between 6 and 6.1 centimeter, you have one more division, this smaller division. See this, it is 6.05 centimeter. This is 6.25 centimeter. Now tell me, what will be the value of this division, this smaller division? Okay, this division, 6.55. Very good, correct. What about this one, this guy? Now I won't be telling you answer, you have to find what is the answer. For this case, I want to know what is reading on main scale. So look at this marker where it is positioned on this main scale. This is 6 centimeter, 7 centimeter, this is 6.5 centimeter. This is 6.1 centimeter, 6.2 centimeter, and this is 6.3 centimeter. Now tell me, this marker has crossed 6.2 centimeter? Yes, true. But look at carefully. It has crossed this 6.25 centimeter mark. Watch carefully. 6.25. Do you feel it? It has crossed? No. It is close to 6.25, but it has not crossed 6.25. It has crossed 6.2. So your main scale reading is 6.2 centimeter. Its picture is something like this. This is 6 centimeter. This is 6.1. This is 6.2. This is 6.3. And between all these points, your marker is somewhere here. So it has crossed 6.2. So your main scale reading will become 6.2. So my main scale reading in centimeter unit is 6.2. Now it's about vernier scale reading. What is role of vernier scale? Scale divides my main scale, smallest division of main scale, into 50 parts. Why I am saying 50 parts? Because there are 50 divisions on this vernier scale. If there are 20 divisions, it will divide smallest division of main scale into how many lines I said? 20 lines. So since we have known what is value on main scale, now it's about knowing what is value on vernier scale. What is role of vernier scale? Vernier scale divides smallest division or smallest separation on my main scale into 50 parts. Why I'm saying 50 parts? Because there are 50 divisions on my vernier scale. So smallest division on my vernier scale. What is smallest separation? See, I told you, look at this paper. The smallest separation is 0.1 centimeter. No, there is one more division. Smallest separation is 0.05 centimeter, or in other words, I can say half millimeter. This is 1 millimeter and this is half millimeter. So smallest division on my main scale is half millimeter. So this half millimeter will again divided into 50 parts. So you get least count of 0.001 centimeter. This is my least count. Least count means the smallest amount of measurement or smallest amount of distance measured by my instrument. So with this instrument you can measure even 0.001 centimeter separation. To put it in perspective, if I write this in value in micrometer value, it will be equal to 10 micrometer. See, 10 micrometer, it's really thin, thinner than your hair. So this is very sophisticated instrument. When you are working with this instrument, please be very careful with this. Its least count is this small. Let's come back here. Now let's come back again here to the vernier scale. We have taken reading of main scale. Now our job is to know what is reading on vernier scale. So to know vernier scale reading, you need to find out which division of the vernier scale is matching with main scale. So there are so many divisions. Which of the divisions are aligning with each other? Perfectly aligning with each other. Zoom out. Which division of vernier scale and main scale are perfectly aligned? So for that, there are various methods to know it. One way is using this magnifying glass. Okay, first of all, let me clean this. I will place it here and I will observe it from here. The first method is with magnifying glass. In case of magnifying glass, you have to put magnifying glass perfectly above this marker. Okay, Now close one of your eyes and the open eye should be perfectly above this scale. It should be perfect. Why perfectly above? If you measure it from here, you get some different reading. You will find that another line is matching. If you measure from somewhere here, you get error. You will feel that some other line is coinciding. If you measure it from here or here, the chances you will get some error. So go perfectly above. Don't see with two eyes because they have different angles. Close one eye, look with this eye, and it should be perfectly above it. So your group members can help you. One of the group members can be here. That group member can tell you, you should come front or go back. One of the team member can go in this direction. That will tell you, go left or right. Right. I'll make sure I'm perfectly above here and I will observe this. So even with it, while taking the reading of main scale, you should follow this methodology. Now I will see main scale reading. Okay, that is 6.2. After I measure this main scale reading, and one more caution, when you are dealing with this magnifying glass, make sure it is parallel to this scale. If it is like this or like this or like this or like this, again you will get error. So it should be perfectly perpendicular. Look at the center of this magnifying glass and your eyes perpendicular above. Okay, main scale reading is 6.2 and I feel that vernier scale reading. Okay, vernier scale reading, it's again we can see. This is one method. You can practice this. The second method is taking photograph. So one of the group members from your group might be having iPhone or any other good camera. So take that for camera. Place mobile phone somewhere here. It should be perfectly perpendicular and the camera should be above. So don't keep like this. Now see, my camera is not perfectly above this. Camera is somewhere here, so it's creating angle. No, camera part should be perfectly above this. Now I will zoom it. Come this side. Come this side and show camera. I will zoom it. Now I can see lines very clearly. Now please make sure camera is not here or not here, not here or not here. It should be perfectly above. And I'm not keeping it very close. If I keep it very close, I'm getting very good result. But I'm not keeping it close. I'm keeping it away to reduce parallax. Not too much away, otherwise I will lose camera quality. Not too much close, somewhere in between. I'm keeping it here. Let me take photograph. Yes. Now look at this photo. This is 6 centimeter. This is 7 centimeter. This is my marker. It's crossing 6.1, 6.2. Okay, here when I see this, I'm able to feel that it is even also crossing 6.25. It is crossing 6.25. Right, so I should write. You should be writing value of division which is crossed. Okay, if it is closer to 6.3, then 6.3 is not answer. The division which is crossed, that is the answer. So 6.25. Now my second task is to find out vernier scale division. Vernier scale division. That means which line of vernier scale is matching with this scale. So look here, I feel this 10th line. This 10th line is perfectly matching with this main scale. So 10th is my answer. Vernier scale division. Now you would say, sir, I feel if you look at this image, and even sometimes students feel that, sir, all the lines are matching. When I see this image, I feel all lines are matching, or not all lines. Sometimes students feel that, sir, multiple lines are matching. And how I would know that? So let me tell you a trick. Let me enlarge this. Here is my 6.25. This is my 6.3. And where is my marker? My marker is closer to 6.25. So it's in beginning. When it is beginning, then any initial line from your vernier scale must be matching. So in beginning means I will just only look in this region, 0 to 20 lines. Somewhere any division will be matching. If marker is not here and here, that means it is toward the end. If marker is here, first of all tell me what is main scale reading. Main scale reading will be still 6.25 because 6.3 is not crossed. 6.25 is your main scale reading. Now in this situation, any ending division will be matching. Any division from the ending. So 30 to 50 division must be matching. If marker is not here, but it is somewhere here, so I won't bother myself to look beginning part or end part. I'll just look at the between part. Any of the division from in between about 25 must be matching here. Okay. But in our case, what is this scenario? The marker is more closer to 6.25, somewhere here. So I won't bother myself to look at the division which are at the end. I will just look here, and I felt that this 10th division is matching. So vernier scale in main scale plus vernier scale will give me total reading, but I cannot directly add this 10 to this. I need to multiply vernier scale division with least count of this instrument so that I get vernier scale reading. So if you multiply 10 with 0.001, you get 0.01. I will be adding this into this. So my total reading would be main scale reading plus vernier scale reading, and it is equal to 6.26. If you do 6.260 centimeter minus 6.149 centimeter, answer would be 0.111 centimeter. So that is the separation between two lines. Ideally on the graph it is supposed to be 0.1 centimeter. So yeah, it's almost closer to that 0.1 and plus some extra digits. So this is how you take reading using the traveling microscope. Now for our experiment, which kind of data we will get? Look at this table. First you will align your crossbar on zeroth fringe. How would I know what is zeroth fringe? There are multiple fringes. There are infinitely many fringes. So you can call any fringe as zeroth fringe. With whatever fringe you are starting, just align your crossbar with any fringe, and that's your zeroth fringe. From zeroth fringe, you will find its main scale reading, let's say 6.25. You found vernier scale reading, that is 10. You multiply it here, 0.01. Yeah, it's in centimeters. See, centimeter, no unit, centimeter, 6.26 centimeter. It's very important to write units in physics. That without unit, quantity is having no meaning. So if you are not writing unit, it's having no meaning, and we cannot consider quantity without unit. Now I will move my microscope with a node and move it toward the fringe. And carefully move it 0 fringe, cos 2, 4 and 5. Please make sure you are not moving to the 6th fringe. You are restricting to the 5th fringe. By mistake, if you go to 6th fringe and when you come back and you are moving node, you add up some error. So you cannot go in reverse direction. You are only moving one direction. Please note this. So while doing experiment, be very careful and move up to the 5th fringe. If you make mistake, please inform us. Don't try to cover up your mistake by manipulation. Please inform us. But it is expected you don't make mistakes. Carefully you move only 5th. In the same process, find position of this fringe. Let's say 0.0. Multiplication, you get 0.0. 3 and the answer would be 6.003. So this is final position or total reading for the 5th fringe. We will do same thing for 10th fringe, 15th fringe and 20th fringe. You will get total 1, 2, 3, 4 and 5 readings. That will total 5 readings. So this is your table number 1. Still you don't know what is fringe reading. But with this data you can definitely find. So once you get this data, you have to come out of the dark room and you can sit with your pen and paper and you can fill out the second table, which will help you to find value of fringe. So So here something is given L, RHS, LHS. These are the values of RHS, LHS. Okay, you may call position of zeroth fringe as RHS. What is meaning of RHS? Zero fringe, 10. Okay. Zeroth fringe, 10th fringe, 20th fringe, 30th, and not 10, 0, 5, 10, 15, and 20. Okay, so position of zero fringe will come here. Not 0, you are supposed to write this value 6.26. Now, what this is right hand side value. Left hand side value is position of fifth fringe. What is value? 6.003. Okay, same way for this fringe width of 5 fringes. What is left value? Position of fifth fringe. So position of fifth fringe will come here, and position of 10th fringe. So I don't know what is position of 10th fringe, so I am just writing 10. For this separation, what is RHS value? Position of 10th fringe. What is LHS value? Position of 15th fringe. Now 15th fringe come here and 20th fringe will come here. For this RHS, LHS. Now if you take subtraction of LHS minus RHS, you get, maybe we can consider taking modulus. You will find some value. The one which we got for our experiment, this experiment that was 0.1 point, no, this one will be similar. It will be something different, but whatever it is, that's fine. And find out distance d. You will get 4 values of it. But is d is your answer? No. What is d? It is the separation between 5 fringes. You don't want separation between 5 fringes. You want separation between 1 fringe. So you can divide this d with 5 to get value of w. So you need separation between 2 consecutive fringes. How many values of w you get? 1, 2, 3, and 4. You will get 4 values. At the end, which value we should take? There are 4 values of w. Which we should substitute here? You can take average value of w. This is your final answer. Take average of these 4 values, you will get average w. Substitute the average w here, and you will get your answer of thickness. Then, this is how you do it. Now let's see actual setup. Come with me in that way. This is sodium lamp. I was talking about. This is sodium lamp. It's closely monochromatic light source. It's only giving yellow light. You can see it. With this small slit, light is falling on this apparatus. If you can closely see, there is something. If you closely see here, there is this apparatus. There are 2 glass plates. One of the glass plate, this end where my pen is touching, there we have kept spacer. The spacer is human hair, and the other end is fixed with rubber band, so the thickness is 0 there, and here thickness is equal to human hair. Can you see this glass plate which is kept at 45-degree angle? So light is coming from this direction, falling on 45-degree angle, so it will fall on our wedge shaped thin film, and here is my telescope. It will observe fringe, and if you want to observe fringe, let's see this. Look at this video. Can you see consecutive yellow lines, black line, yellow line, black line? Okay, those are our wedge shaped thin film fringes. Those are parallel fringes. Okay, we are finding it difficult to focus it, but when you observe it with your eyes, you will be able to see this beautiful pattern. Can you see that cross wire? And there are dark and bright fringes. We want to find W, that's why we will be aligning our cross wire on either bright fringe or dark fringe. But it's more easier to align our telescope with black fringe because it's more sharper. So now it is aligned with black fringe. I will call this fringe as 0th fringe. Let me move to the 5th fringe. So closely 1, 2, 3, 4 and 5. I moved slightly more than 5th fringe. So I cannot go back and come here. It will add up some error. So if you make mistake, you have to start it again. 0th position, I'll align it to 0th fringe. I will take photograph or using my magnifying glass. I'll find out the position of 0th fringe. Now I will carefully, slowly, first, second, third, fourth, and now very crucial part, 5th fringe. Okay, this is fine. I'll again take photo and find out the position of 5th fringe. 6, 7, 8, 9 and 10th. I'll come back, I'll take my away. We will take reading of this main scale. Okay, we will take main scale reading, we'll take vernier scale reading, and we find out what is the position of 10th fringe. This is how we take position till 20th fringe, and that's how we can fill our table number 1. If we take, now we have all information required for table number 1. Now we can come out of the dark room, we can sit on the table, central table, and we can create the second table, table number 2. That table number 2 will give us value of W. That W you can substitute to the formula and you can find T. What is T? Do you remember what is T? T is the thickness of spacer. And what is the spacer in our case? Human hair. So by this experiment, you will be able to find thickness of human hair. While working this experiment, you have to take care of few things. Okay, this experiment is very sensitive. I told you what is least count of this traveling microscope. It is 0.001 centimeter. That's very small distance. 10 micrometer. 10 micrometer is very thin. So if you are working here and by mistake if you touch table, it may change few things. Just don't make this computer, this table move. Some people have habit of working like this. Okay, so if you are putting some weight, it may change your table and your position is changed. If you are misplaced, then you have to again start with 0th fringe. And it's very tiring task. Okay, don't do that. Sometimes the people who is observing, they have a habit of holding it like this. So when they are releasing their hand, it might be moved. If your height is smaller, take help of some stool, stand on that stool and see what's there. Sometimes that person is very careful. They are looking like this, okay, that's good. But their teammates are notorious. They are writing readings on notebook, but they are writing reading on notebook. When you write, table will move. So when you are working with this experiment, you have to be very careful. You have to make sure the table is not moving. Alright, otherwise your hard work will be ruined. You have to start again. So please make sure, work calmly. After watching this video, if you have any doubt regarding this experiment, how theory is working, how any procedure is done, any doubt regarding apparatus, you can ask us when you come in the lab. Okay, thank you so much. See you in lab.